All right, today we are jumping into polynomial division. And I get it, the name alone can sound a little intimidating, like long division but with letters. But trust me, this is way more than just a math chore. It's actually a super powerful tool for breaking down complicated problems. And we're going to use it to solve a very specific puzzle. So, here it is. Picture a box. You know its volume, you know its length, and you know its width. But there are all these messy algebraic expressions. The height? That's the missing piece. So how in the world do you find it? Well, that's exactly what we're here to figure out. And this isn't just some made-up problem. This is the kind of thinking that goes into real-world engineering and design. So to solve our puzzle, we're actually going to start by rewinding a bit, back to something you definitely already know. Good old long division. Seriously, don't let all the x's and the powers throw you off. At its core, this whole thing is built on that same simple idea. Okay, let's take a look. On the left, you've got the long division you probably learned back in grade school, right? And on the right, you've got polynomial division. But just look at them side by side. The structure, that classic division bracket, it's the exact same thing. We're just swapping out simple numbers for these algebraic terms. The process, the pattern, it's all going to feel very familiar. That's our foundation. First up, let's talk about the classic method, polynomial long division. I want you to think of this as the Swiss Army knife in your math toolkit. It's dependable, it's versatile, and it will get the job done every single time, no matter how gnarly the polynomial looks. What's really cool is that this whole process boils down to a simple 4-step loop. You just repeat it over and over. You divide, you multiply, you subtract, and you bring down the next term. That's it. It's a rhythm. Once you get it down, you just cycle through those 4 steps until the problem is solved. Now, before you even start, there are 2 golden rules that will save you a ton of headaches. First, you've got to write your terms in descending order of their power. You know, x to the 4th, then x cubed, x squared, and so on. If you mix them up, the whole process falls apart. And second, if a term is missing, like if your polynomial jumps from x fourth to x squared with no x cubed, you have to pop in a 0 as a placeholder. This keeps everything lined up perfectly, just like in regular division. And here's the logic behind why it all works. It's called the division algorithm, which sounds way more complicated than it is. It's really just a formal way of saying something you already know instinctively. If you divide 10 by 3, you get 3 with a remainder of 1, right? Well, how do you check that? You multiply the divisor, 3, by the quotient, 3, and add the remainder, 1. And yep, you get 10. It's the ultimate way to double-check your answer and make sure you got it right. And this brings us to the big aha moment. When you finish all that work and your remainder is 0, that means something huge. It means your divisor goes into the dividend perfectly with nothing left over. In other words, the divisor is a factor of the original polynomial. And finding factors? Well, that is the key to breaking polynomials down and solving equations. This is where division becomes a power tool. Okay, long division is awesome, but let's be honest, it can be long and a little tedious. So for the right kind of problem, there's a shortcut, a pro move. It's called synthetic division, and it is way faster and cleaner when you can use it. But here's the catch. Synthetic division is a specialist. It only works in a very specific situation, when you're dividing by a simple linear factor, like x minus k. That just means your divisor is simple, like x minus 2 or x plus 5. So, while long division is your universal tool, synthetic division is the precision scalpel you pull out for the right job. And you can see immediately why it's so much faster. Look, no variables. You just pull out the coefficients. You bring down that first number, and then you get into this simple rhythm. Multiply, add, multiply, add. You just work your way across. The numbers in your final row are the coefficients of your answer, and that very last number on the end, that's your remainder. It's so efficient. All right, so now we have our power tools, the trusty, all-purpose long division and the speedy, precise synthetic division. It's time to put them to work and finally solve that puzzle we started with. Okay, let's circle back to our box. We've got that big expression for the volume. We know the length is 3x and the width is x minus 2. The mission, find the height. And since volume is just length times width times height, we can work backwards. To find the height, we'll divide the volume by the length, and then divide that result by the width. So let's do this step by step. First, dividing that whole volume expression by the length, 3x, is pretty straightforward. It just simplifies things down to x cubed minus x squared minus 11x plus 18. Okay, now for step 2. We take that new polynomial and divide it by the width, x minus 2. And hey, look at that divisor. It's in the perfect form for a shortcut. So let's use synthetic division. We put 2 in the little box and write down our coefficients, 1, -1, -11, and 18. Now we just follow the pattern. Bring down the 1, multiply by 2, add to -1. Multiply the result by 2, add to -11. One more time, and what do we end with? A remainder of 0. Perfect. So what do those numbers on the bottom, 1, 1, and -9, actually mean? Well, they're the coefficients for our answer. We started with an x-cubed polynomial, so our answer will start with x squared. And that means the height of our box is x squared plus x minus 9. And just like that, puzzle solved. We took a really complicated-looking problem and used a clear step-by-step process to find the answer. So we've seen that division is an incredible tool for breaking down polynomials. But let's think a little deeper about what we found. That 0 remainder, it told us we found a factor. And if you know a factor, you're just one step away from finding a root. For instance, if x minus 2 is a factor, that means x equals 2 is a root of the equation. So that leads to a pretty interesting question, doesn't it? Can we use these exact same division techniques to go hunting for all of a polynomial's hidden roots? Now that's something to chew on.